Hello, in this video we are going to talk a bit about commutators because we're going to need it when we start talking about solvable groups. So we've already seen the definition, but the definition of a commutator given a group G and elements X and Y in G is just this product. And the point is that the commutator is the identity if and only if X and Y commute with each other. And of course you could go a little bit crazier given two subsets of G, A and B. You can talk about the commutator subgroup. So this would be the subgroup generated by commutators A, B, where A is in A, B is in B. And so it's worth pointing out that this is definitely not the same thing as the set of all commutators. Because in general, there's no guarantee that the product of two commutators is also a commutator. So you're not guaranteed that this set's closed under multiplication, so it's not necessarily a subgroup. But you can always consider a larger subset by taking the intersection of all subgroups that contain these commutators, and that is a subgroup, and they call this the commutator subgroup. And the most important examples called G prime, it's the set subgroup generated by all commutators in G. So we're going to prove some basic facts about commutators and commutator subgroups that we're going to use when we study solvable groups. These are listed as Proposition 7 in section 5.4. So we're going a little backwards, but that's okay. And the first fact is that multiplication commutes up to multiplication on the right by the commutator. Of course, here I should be careful. The textbook does things differently than I expect. They put the inverses first. And yeah, if you do this calculation, it's clear. X inverse cancels, Y inverse cancels, and you're left with XY. So yeah, that's true. The next one is that H is a normal subgroup of G if and only if the commutator subgroup of H with G is a subgroup of H. Well, let's think about this one carefully. What happens when H is normal in G? That tells you that G inverse HG is an H for all H and all G. We'll come back to that thought though. So let's take something in the subgroup generated by the commutator. So take H and G and G. Well, let's look at this commutator. Looks like H inverse, G inverse, HG. Oh, but we notice this last three terms together are an element in H. And H inverse is also an H, so this product is an H. So what we see is that this commutator is an element of H for all H and G and G. And so that means the set of such commutators is a subset of H. In particular, the subgroup generated by the commutators must be a subgroup of H. Because one way to define the notion of subgroup generated by a set is to, by definition, the intersection over all K. K is a subgroup of G. S is a subset of K. If you take this fact, well, H is one of these factors here by this fact we just showed. And so that's enough to show that the subgroup generated by the commutators must be a subgroup of H. Conversely, if the commutator subgroup were a subgroup of H, and we take H and G, we already have now that HG, this commutator, is an element in H, so let's call it H double prime. So if H double prime is H inverse, G inverse HG. So that means H double prime H is G inverse HG. So that tells you G inverse HG is an H, because that product on the left-hand side is an element in H. And so that means H is a normal subgroup of G. Fact 3, which is kind of big, is that if you take an automorphism of G and X and Y and G, then the automorphism is going to take the commutator and send it to sigma X, sigma Y. In particular, it sends commutators to commutators, and so that tells you that sigma of G prime has to be G prime, because that's a subgroup generated by all commutators. And so in particular, G prime is characteristic in G. Another fact we will show is that G mod G prime must be abelian. Note here, a claim I'm skipping here is that this is a, we'll do the proof a little bit more careful. So what is the commutator? It's X inverse Y inverse XY. That's just sigma X, because you're dealing with a homomorphism, sigma Y inverse, sigma X, sigma Y. And lo and behold, that's just the commutator of sigma X with sigma Y. Because it's a bijection, we see we've mapped a commutator to a commutator. But let C be the set of commutators. We can see that sigma maps the set of commutators to itself bijectively. As follows, you send xy to sigma X, sigma Y. And the inverse would be to send xy to sigma inverse X, sigma inverse Y, because the inverse of an automorphism is an automorphism. So you need that to be able to say that the image of this G prime is actually G prime, because you send every commutator to a commutator and you manage to get every commutator in the image. And then you're taking the subgroup generated by all commutators, so you have to get the same group. Finally, why should G mod G prime be abelian? Well, take X G prime times Y G prime. That's XYG prime. By property 1, we have this commutativity here, where you can replace xy with yx times the commutator of x and y. But the commutator of x and y is an element in G. Statement 4 says that G mod G prime is the largest abelian quotient. And it's kind of weird to state what that means precisely, but this is the way they choose to state that. That means any other abelian quotient you could come up with, the thing you're quotienting by must be a supergroup, or G prime is a subgroup of it. So if H is normal in G and G mod H is abelian, then G prime is a subgroup of H. The converse turns out to also be true. If G prime is a subgroup of H, then H is normal in G and G mod H is abelian. And there's another way to state this in terms of homomorphisms. If you have a homomorphism from G to any abelian group, A, then G prime actually must be a subgroup of the kernel. Moreover, you should be able to set up a diagram like this, which basically means you can create another homomorphism from G mod G prime to A, such that you get the correct compositions to work. And the book points out 5 is just another way to state 4, but I'll state why that is true. That's because, well, let's see what happens. You already know that the image of G is isomorphic to G mod the kernel. And lo and behold, what must be true? Well, the image has to be abelian, and so this is abelian. So by 4, which I haven't proven yet, that means that you know that G prime is a subgroup of the kernel. So that takes care of that part. The other part has to do with the fact that in general this statement is true. Whenever you have a normal subgroup of the kernel, you can construct this homomorphism. That has nothing to do with abelian groups. How do you do that? Well, you just have to prove well-definedness, and two things are equal if you check the well-definedness criterion, and it ends up working because the only way two things are equal, have the same coset, is if the product, if gk were equal to g prime k, that means that g inverse g prime is in k, which means it's in the kernel. And you can use that to show that you get a well-defined answer. Alright, so why is 4 true? Well, let's assume H is normal in G, and G is abelian. G mod H is abelian. But we want to prove G prime is a subgroup of H. We're going to do, well, G prime is generated by commutators. So what we want to claim is that the commutator times h is equal to h for x, y, and g. And here we're working in the group G mod h. Why would we want to do that? Because that tells you that all the commutators are elements in H, which means that H contains every commutator, therefore it contains G prime. So let's calculate this commutator. It's x inverse y inverse xy. But since you're working in this quotient space, that's also x inverse h times y inverse h times xh times yh. G mod h is abelian, so I can actually commute cosets. And now I've got cosets paired up with their inverses, so I just end up with 1 times h. So that tells me what I wanted to show. G prime is definitely a subgroup of h. So G mod G prime is the largest abelian quotient. When I was in graduate school, I actually had studied this type of construction. They called it the abelianization of G. And, it was much... In research, we had studied it, but I had never gone through the understanding why it was called the abelianization and why it was the largest one. This is why, because it's the largest abelian quotient there is of the group you started with. Now, the converse direction is not that bad. I mean, you're looking at G prime as a subgroup of H. We already know G mod G prime is abelian. In particular, every subgroup is abelian, so H mod G prime is too. And this also means H mod G prime is normal in G mod G prime. Applying the isomorphism theorems, this tells you that H is normal in G. And then you use the fact that G mod H is isomorphic to G mod G prime, quotient out by H mod G prime, which are both abelian groups. So that's enough to tell you that G mod H is also abelian.